Thank you. So we've seen a talk about the component model, and we saw a talk about Golem, so I will just try to connect the two and talk a little bit about how we build on top of the component model and what kind of use cases it makes easy for us. But first, let's see again what Golem is. And I will say Golem is a WebAssembly-based worker execution platform that implements durable execution in order to provide high reliability for your programs. And of course, this durable execution property is the most interesting part of Golem, but that's not what I will talk about. So let's just focus on it being a WebAssembly-based execution platform. And as John already showed, you can think of it as something that runs a couple of workers. And each of these workers are instances of Golem components, and these Golem components are nothing else than WebAssembly components. So let's talk a little bit about WebAssembly as well. First about the core WebAssembly standard. And the core WebAssembly standard defines a low-level, high-performance bytecode with things like linear memories and function pointer tables and functions which are only taking numeric parameters and giving back numbers as results. So it's a quite low-level thing. This is an example of the textual representation of a WebAssembly module. It has function type definitions, and it has the actual code. And on the bottom, it has some exports. It exports the memory, and it has a named export of a function. So if we have exported functions, that means that we can do an external call to a WebAssembly module. But to do that, we need some kind of a contract. Why? The reason is, so we don't know without a contract what is the meaning of these numeric parameters of these exported functions. Are they pointers? Probably they are. But if they are pointers, what's the required memory layout? Where should I put my data before I'm calling these functions? And the core WebAssembly standard is not specifying this. It's something you have to figure out on top of it. And that's where the component model comes to picture, and it defines many things. And one of these things is it defines higher level data types for you, for example, lists and records and variants and a lot of more. And in addition to that, it also defines how these higher level data types are mapped to the core WebAssembly standard. How you can pass them as parameters, how you have to lay out them in memory, and so on. And another thing that the component model defines is this higher level abstraction called a component, which has imports and exports, and these imports and exports are organized into interfaces. And a very nice thing in the component model is that it also defines composition of these components. So if you have matching imports and exports in two components, you can construct a bigger component out of them, and that eliminates these matching imports and exports, only leaving the rest on the bigger component. And two other things that extends this ecosystem of the component model. One is the WebAssembly system interface, which defines component model interfaces to things on the external world, like working with files, logging, doing HTTP, generating random numbers, and so on. And the last thing I have to mention is the existence of these binding generator tools, which are taking the component model interfaces and can generate you statically typed code for your chosen programming language to work with these types and interfaces. There are binding generators for Rust and Go and C and C# and so on. And maybe the future is to have native support for the component model in programming languages. There is at least one work in progress language called Clo, which is natively supporting the component model, but maybe some other languages will choose to do that in the future. So the first thing that Golem is doing and is heavily relying on the component model is worker invocation. So as I said, Golem is running workers, but these workers are not just something that you fire up in the cloud, and it starts running until completion. A worker is something with a well-defined interface. It has callable functions. These callable functions have type parameters and the return value. And this is exactly what a WebAssembly component is. So that's, with that, it means that we can just create a WebAssembly component, a single WASM file, and upload it to Golem. And Golem can analyze this component and figure out what the exported interface of your worker is automatically. And of course, it's not that simple as it may look like. Sometimes it is simple. This is a textual representation of a WebAssembly component. Sometimes you just find a top-level export section in it, and then it refers to something like instance 11 here. Then you find instance 11, which will refer to a function 17 and follow all these links and eventually collect all the data that describes your component's interface. And sometimes it's much more difficult because, as I said, components can be composed into bigger components, and this is hierarchical. So sometimes you run into these aliases, and you have to go into inner components and then a component in the inner component, and that can refer to exports and imports of other things. So it's not that simple, but it is possible to fully reconstruct the interface of a WebAssembly component. And this library that I have a link on the bottom too is a Rust crate which implements all this and open source. So if you ever need to do something like this, please check that out. OK, so the next thing. This worker invocation took advantage of components having exports. But the components also have imports, and those are basically the dependencies of your Golem component. So let's imagine it can depend on, for example, the WASI clocks interface and using HTTP and using a key value store implementation. And one thing that Golem has to do is, of course, having an implementation for all these interfaces. That's how it can run your component. If it's not having an implementation for something your component depends on, then of course you cannot run it in Golem. But an interesting thing is you can also use component composition to eliminate some of these dependencies. So for example, if you don't want Golem to implement the key value store for you, and you have a third-party library that implements this WASI key value interface, and it's compiled to a WebAssembly component, you can just compose your Golem worker with this library. The key value store interface got eliminated, and you can still run it in Golem, and it will use your chosen third-party key value store implementation, which is something nice. And the last thing that I want to show is how we use all these techniques to implement statically typed worker-to-worker communication. So in this case, let's imagine we have a worker A and a worker B. These can be different WebAssembly components implementing an interface A and an interface B. And the question is, how can we call worker B from worker A? And an obvious answer to that is to just use this worker invocation API that I was talking about. So Golem already analyzes all these running components and knows what they are exporting and provides an HTTP API to invoke those. So we can use this from worker A by using WASI HTTP to do the HTTP request. And this would work, but it's not very convenient, and it has many flaws. First problem is that you have to do this through this HTTP API, which means you have to construct the request, assemble some kind of a JSON request body, and do the request, and then parse the response, and so on, just for a single worker invocation. So to make it less redundant, we would probably have to provide a wrapper library for all this to each language that we want to support. And even if we've done that, it will be still having low performance, because even if the two workers that are trying to communicate are living in the same process, it would go through many network hops and do all this serialization and everything. And the last thing is that it would be untyped. You have to convert your request into JSON and then parse the response JSON and not having any static type safety on it. So let's try to do something better. And of course, we should think of something that involves the component model. And to do that, first, let's see some more real examples. Worker A will be something that we call the caller, with exporting a single function that just returns a number. And the component that it tries to call is called a counter, exporting an increment and a get function. And yeah, we want to call this increment and get function a couple of times from the test function. So the first idea that we can have is to just use the component model, import the counters API into the caller. And that would, with the help of the binding generators, allow us to just use a regular function call to call these increment by and get functions. And we can say that Golem solved the whole problem for us because it knows that we have a worker B which implements the counter interface. It knows that we are importing it. So it could just magically make it happen. But the problem is it cannot, because there can be millions of workers running and each implementing the counter interface. With this approach, we don't have a way to specify which worker we want to talk to. But with a small change, we can introduce a third interface, which we will call counter stub. And it's almost the same as the counter, but we wrap the whole thing in a with resource. And the resource is something that has a constructor and can have methods on it. So first you have to construct by passing this location parameter to it. And the location will identify which worker you want to talk to. And after that, you constructed the resource, you can just call the counters originally exported functions, but it will now have an associated location where we want to do the remote call to. And we change the caller to import this counter stub instead of the original interface. And with that, if we are implementing our caller component in Rust, it will be just a very simple code that creates the counter and calls these functions on it, very nice, statically typed, and so on. But if we do this and upload it to Golem, it will still not work. It will fail with an error, and the reason is that now our component depends on the counter stub interface. And the Golem is not implementing the counter stub interface. It has no idea what it is. So what can we do? Well, another thing that Golem does implement is called Golem RPC, or WASM RPC, a WASM RPC resource packaged into the Golem RPC with package. And this is very similar to what I was doing before. It's a resource that has a constructor with a location parameter, but instead of the user-specific concrete functions, it has a general purpose invoke and the wait function, and also an invoke, by the way, which takes the function name as a string and the function parameters as something as with values. And the with value is also defined in this package. It's just a component model way to describe component model values within the component model. It's just a type definition for describing arbitrary values. So the idea is to use, again, component composition to solve this problem, because, as I said, with that you can eliminate dependencies. So the idea is we have worker A, depends on the counter stub interface, and we have some kind of a counter stub component which implements the counter stub interface and compose the two together. The composed one no longer depends on the counter stub, but it depends on WASM RPC, and with that we can invoke worker B. How would this counter stub component look like? If it's implemented in Rust, it will be something like this. It has this constructor that takes the location URI And that just delegates this thing by constructing a WASM RPC resource with the same location. And then it has an implementation of each exported function, for example, increment by, and just delegating the call to this invoke and await thing, which takes the function name as a string, and you have to encode the values with this with value thing. But how can we get this counter stub thing? We don't want to write these by hand, definitely. So the good news is that you can just generate all these stubs only from the interface definition of the component that you want to call. In details, it means first you have to generate and build this stub component by first parsing the interface definition of the target component, generating a new interface definition, and then generating some kind of source code that implements this. We are currently generating a Rust source code, but it doesn't really matter because we immediately build the whole thing into a WASM file. And the next step is adding this stub as a dependency to the other component that you want to, where you want to do the remote call. And that involves things like manipulating these with dependency directories, and if it's a Rust project, then you also have to manipulate a cargo file, but it's really just moving files along and adding some dependencies into them. And the last step is composing your generated stub that was built in the first step with your actual compiled code. And that's just the regular component composition. There are tools for that, for example, WASM tools compose. And the resulting WebAssembly file only depends on WASM RPC and the other things you were depending on, but not on the stub, so you can run that, upload it to Golem and run it. There is this other published open source library called WASM RPC, which implements all this and some other things. For example, it has a Rust implementation of all these value types involved and conversions between them, look like this. It defines this builder API, which is used by the generated stubs to construct these with values from your typed values in an easy way. And it has the opposite, which is used for constructing back type values from the with value result values. And it has all kind of implementations of various serialization formats and adapters to WASM times own representation and so on. And this library is used by Golem's CLI tool as well to wrap these steps to generate the stub and add this dependency and so on. So that's exposed as a CLI command as well. And in case your components are all in a single Rust workspace, then there is even support for generating a cargo make file that even further automates all these steps for you. But it's very important that this is not Rust specific. There are, of course, some Rust specific features like this cargo make thing and manipulating cargo files. But it works with any language, and it can be even makes like your one component that calls the other. They don't have to be implemented in the same language at all. So that was it. And I hope I showed that WebAssembly components are self-describing and composable, and this allows a lot of new interesting applications. And finally, I think that by us building on these standard technologies makes that every improvement into the WebAssembly ecosystem is an improvement to Golem, but hopefully it's also the other way around, and some things that we are creating can benefit the whole WebAssembly ecosystem. Thanks for attending.